So basically everywhere throughout from the power generation to till in the user side till the end side actually, which means you need a active power, you need a reactive power, right? So in the grid there has to be a reactive power energy back and forth. It is required from the transmission network to power generation. That is very common, right? And whereas in the motor, like in the end user side, because there is no equipment which produces reactive power, basically all like, but these equipments needs reactive power. Where from where they will get it, it has to be come from the network only. So that is why here you see that here there is a possibility, sir, reactive power back and forth will be there. But here in the distribution side, only it will draw reactive power from the transmission network. So with this itself, we can say that reactive power actually it is taken from the grid itself. That is why because of this reactive power, like there is a equipment and everything, it is oversized. So that is why utilities are putting a penalty onto it, right? That is one thing, right? Let's try to see what are the consequences and etc, right? So let's try to understand now. So to understand this, because circulation of reactive power in electrical network, let's see that one is technically we have to see it, another one is economically we need to see it, right? When the higher reactive power means higher apparent power. So when the higher apparent power means higher current, right? We'll see that through calculation, you will understand that. Okay, that is one thing. You see that when the circulation of the when the circulation of the active power over time, uh, what we call is active power. I mean energy, right? Generally, energy what we are defining it with respect to the time kilowatt hour, right? The same manner for the reactive power we call it as a kVAR H, right? So this is the basic, right? So we'll see other impact, why it is, disadvantage. We'll try to see that. Okay. And these are the disadvantages. Let us try to understand that how, why they are telling this, all those things. Okay. Disadvantages, all those things. There is, so we'll keep this point. Now, with that, I will open that tab. That I will try to open it up so that you will understand that certain points. Let's wait. Okay, so let's take one simple file. Okay, so let me. So we'll try to look into how this works. Okay, why it is very much so concerned. We'll try to see that. So to do that, I'll try to add. I'll try to add certain buses here. Okay, so for the simplicity. Okay. Mm, okay, so this one I will make it like I will make it like I will make it like make it like that. Okay. So let me add some, dummy data actually. So we will assume that, right? So we'll have it like that. So this is what we are having it. So let's take some. Okay. So in this way, what we will do, we'll add one more information here. So I'll try to model it here so that it will be easy in the later stage to understand better. That's why I'm doing it. So let me add one more LV sideways. This is a typical, system. We are trying to understand that what is real, power factor index, right? So let's say that this is 2 MVA, and let's say that this is LV side. Okay, so let's add the symbol, and it is solidly at the. So we will have this one, and we'll ensure that this is 0. Great. So we have this one actually. So let's have this actually, right? So this is the typical network. So we have a 2 MVA transformer. So let's add some load actually. So let's add some load. So I will go here. So here, if you go, I will add some motor loads. As far as CTAP concerned, like when you add lumped load, there is something called constant KVA, constant impedance, right? So constant KVA means constant power, right? That means that is the motor load. So in this case, we will assume that there are some motor loads, right? So 2 MVA, right? So let's give some, 1600 kilowatt, and let's say that this is actually 80 percentage of that, right? More 80 percentage of this load is like that. So let's give that one. Okay. So we have a 2 MVA, and we have a load of 1600. Okay, 1600. So let's keep it like that. So this is one. In the 11 kV side, let's add a few more data. So this is 10 MVA, right? So already we have 2 MVA. Let's add 8 MVA or 6 MVA. Or basically, let's give some random, right? So this is again the motor load is 80 percentage, and that constant impedance load it is about 20 percentage, right? So let's add. So now you know that total load for this 2 MVA transformer is totally 1600 kVA. So for this 10 MVA transformer, what is the total load? Here 7 MVA, here 2 MVA. So altogether, if you add it, it will be like 9 MVA, right? It will be like 9 MB. So this is the network for us to understand this concept, right? So I am just going little bit. So let's run that. Let's try to run that. So let's try to run that. I will explain that what exactly is happening. So when you run it, when you run it, like, can somebody tell me that what is the total load at the moment it is connected at in the 10 MVA transformer? Can I get some answer, quick answer in the chat? So considering the present situation, can I get some quick answer from the chat so that let's make it little interactive? Anyone? Yeah, Sayed. Yeah, 7 MVA. Yeah, Sayed, actually, there is a 7 MVA in the 10 MVA. There is a one more load here also it is there, right? So that means 7 plus 2 MVA, around 9 MVA total it is there, right? Yes. Okay. Yeah, thanks, Santosh, for putting it. So let's run this actually. So I have run the, basically I have run the load flow here. So there are, but what you have seen is connected load. But what is that you are seeing it? No, this is what the actual load which is flowing. So let's add a unit to that. Okay, let's add a unit to that. So you see that what you're seeing everything in apparent power, right? So let's make it in apparent power. So let's try to understand that what exactly is going on. Okay, you see here, I'll try to make it a simplified one. In this 2 MVA, the total load apparent power, what is that it is drawing from the grid is 1600 kVA. The total current which is required, this is a lump load. That means it's a group of loads, group of motors and other, constant current loads, constant impedance loads actually. So, which is 2310 amps, which is it is taking out from the grid, and it is apparent power. But if you look at, if you go with kilowatt and kVR, considering the present situation, the active power it is drawing from the grid is 1280 kilowatt, and whatever that, because of the total motor loads, no, because of that motor loads, we are also drawing a reactive power of 959.9 kVR, right? Now, someone like, why it is why this 959.9 kVR is coming? It is because of the motor load. Okay, 80 percentage of that motor load. Let's try to see what happens now. So now I made this loader 0. Okay, let's try to see that how much it is drawing. Okay, let's try to rerun that. So when you rerun it, again we are getting like that. Let's see that why, how much we have put a power factor. So we have put this one actually. So let's put 100. So let's see that what happens now. You see, when the power factor is 0, that means it is considered all the loads, it is considered as a resistive load. That means it draws only active power. But in a real scenario, it's a combination of loads. We may not know exactly what is the trend, etc. So there will be a always difference. So in a typical, like 80 percentage will be there. Even if you say that it is a 70 percentage means, earlier it was coming around 956, right? Now you see here itself we can say that, you can see that, you see it is taking even like let's keep it like 80 is to 20. So that means from the induction motor, you are getting 914.1. From the other static loads, we are getting 228.5 together. So that means now you see, now you will draw active power like 1139 kVA from the grid, which means this reactive power is drawn from the grid, these loads, because of this power factor. Now now what you will have to understand from here, lot of reactive power we are drawing here. So let's try to understand. So here 1139 kVA, here that's the same. Now you see that now after 1139, like suddenly here the total active power required 1,117. That means 1,117 kilowatt only is required. But suddenly there is another requirement suddenly, because whatever there is no other extra load. But why this is increased actually? 1139 kilowatt, 1227 kVAR. Why it is increased? Anyone tell me? Because there is a loss in transformer. Okay. So let's try to right. So let's try to add this this one, right? So what happens now? So what happens now? So when you sum it up, you see, let's try to do that. So 117, it's active power, right? So let's put active power. So additionally 14.6. So together, if you do it in ETAP, you can do it directly. So you can visualize it. That's the total active power, including transformer loss it is consuming. Even for the transformer, by default, internally, because of this, impedance and etc., it also consumes some reactive power. Okay, so let's look at this Q. So originally what we need 1139, right? And because of this including transformer, that means 87.7 you need actually, right? So together if you look at, so that is 1227, which is nothing but 1226.7. Both are same. So this is our final power, reactive power requirement from the grid. Now, if you carefully in this way, if you go slowly up, now you together you sum it up. Okay, so that means this one, and there is one 5576. If you sum it up, right, 6707.6, which is 6708. It is coming, right. So similarly for the Q1, if you make it 4182 plus this one, if you add it, no. So let's put this one. So let's add this and this. So which means 5409, here 5408, right? So this is at 11 kV side, right? This is at 11 kV side. So this is at LV side. Okay, this is at LV side, right? So this is how the reactive power consumption is coming. But when you go up here, you will see that including the transformer losses, that you have to accommodate from here. So and let's see the power factor now. Let's see the power factor now. We didn't see the power factor rate, right? So let's see what is the power factor from here. So for the power factor, you need to enable this one in this. So let's enable this actually. Can you guys see that? Can you guys see that here? When we put power factor here it is a 70% power factor, right? And because of that, this much is coming. But when you go up slightly, so because of this LV side, whatever that power factor, and including that this additional losses, again here the power factor is getting reduced, right? Now in the 11 kV bus, if you look at 80% of power factor plus 67.79 power factor together, if you sum it up, so we'll be getting something like that. Here you don't put directly, it will not come. So here you need to use the complex form to get the actual numbers, right? But the current, if you add it, you will get it the exact number, right? So here together 77.84% of the power factor, right? Now because of this power factor and everything, no, because of this power factor and everything, no. So let's try to see that. So to make a difference, I'll just here what we have done. We have done 70%. Okay. So here what we have done. Here 80% we have given. Okay. So now in this scenario, what I will do, I'll put 99%. Okay. I will put maybe, let's say I put 95% just for the discussion. Here also I will go with the 99%. I mean 95%. Okay. So let's see what is the impact in that. So both are same case. What if there is a power factor is high? What is going to happen? That's what we are trying to see it, right? So that's why we are doing both side of simulation so that you can understand better. So now you see that. Now can you guys see that what is the difference? What is that you are able to see that, guys? What is the difference that you are able to make out here? Anybody can tell? Anybody can tell that what is the difference you are make out? So here you see that this is, this is, this is, this is, all those things you could see it literally, right? All those is you can see it literally. See, this is a low power factor. This is the higher power factor. Because of this higher power factor, you see that here the current requirement what you need is 231 amps, 2319 amps. But here you see that there is a huge reduction of current, right? Here what we need is 2261 amps only, right? 2261 amps only. Then same thing will reflect in all other network, right? Right? In other network, right? See, the transformer, there is no much difference, but still it matters. Like it is, there is a slight reduction in that, right? Because of this higher power factor. Here also you see that. What we need here is 457.2 amps, but here what we need is only 451. That means there is a huge reduction in the current. There is a reduction in the current literally, which you can see that will have a huge impact on thermal aspect of the cable, because definitely it is going to reduce the thermal impact on the cable actually, right? So that is what it is actually. So let's try to see in terms of apparent point of view, apparent power point of view, right? So now what you are looking at is a apparent power. You see here, when we have that power factor here, you see the finally the grid. What you are taking is 9106 kVA. But here, because of that improved power factor, because of the higher power factor, see, though, like you need 9106, but here what you need is 8987, which means basically we are reducing the apparent power requirement, which means you don't need to take more apparent power from the grid. This is the reason utility companies, when you draw more apparent power from the grid, so that is where these people are, you know, uh, one second, one second. Here you will see that reactive power. Here you see that reactive power. Can you see that? Here, when the power factor is low, you see here, we are drawing more reactive power from the grid. But when the power factor is very high, you see that? Can you see that? You are literally reducing the reactive power from the grid. That means your utility, they don't need to support reactive power to your network, because your side is most of the loads are in like already it is taken care of. It means you are running the plant in very high power factor. That means we are literally reducing the burden to the utility or EB supply or EB companies, actually electricity boards, right? That is why for the higher power factor we are getting the less tariff, right? When there is a low power factor, we are getting the high tariff from them as a penalty, right? Right. Now you are able to see that, no, literally, like though, like we are saying that some disadvantage, higher energy consumption and cost and etc. Okay, but this one you are able to see it in the in the ETAP, right? This is how you have to visualize the things. Okay, so now we have not included some cables and etc. I mean, I have not added cables actually. If you have added cables, you will see the voltage drop as well. So that you will also see that a lot of drops also, voltage drop also, it can be minimized. This is the advantage when you are improving the power factor actually. Okay, so some of the things, it may not be directly visible to us, but certain things that you need to work out. And if you if you find the right capacitor factor, sorry, capacitor bank, if you put it, no, so there will be a huge reduction in the electricity bill. And of course there is we need some capital investment, no denying in that, but that will help us to reduce your electricity bill in a very high level actually, right? So it is very, very, very important, guys, right? So guys, you are getting it, no? Why now you understand, no? Low power factor means what are the disadvantages that